Happy Carmen, and this is my Physics 2211 Lab 2 of Projectile Motion. Content covered: purpose, procedures, then physics, then code, and error, and any questions that may arise. Purpose of this lab is to be able to compare the differences of a real-life model projectile with two computational models, one which includes gravity and the other one includes gravity plus drag, force of drag. Equations to know, according to these are all according to Newton's second law of motion, and you have to know the velocity update formula and the position update formula, and then don't forget about drag and force of gravity. Instructions: things needed: an object like a ball, phone or something to record, something to measure, an app like Tracker so you can track the position of the object through a video, laptop and glow script to write your code. Procedure: record a video and where you throw the object and let it go both in the Y and the X direction. It's a projectile. Use the laptop and go to glow script to create code that would demonstrate the object's movement in an optimal environment. This is the starter code we were given, so there's that. And then grab all the data points so you can compare your findings. This is my video. All right. So for the computational, the gravity only, we found the velocity vector by using the first timestamp and then using the equation v equals change in r over change in time, and then we plugged in all our values and got that velocity vector. Delta t, it was just that's how many steps the experimental, like real life one, gave us. B is 0 in this occasion because it's gravity only. I did add the equation here, but I made sure to only include gravity and not drag. Velocity update formula is just the one from the beginning. Ball dot velocity equals ball dot velocity plus Fnet, which in this occasion is just Fg over mass of the ball times delta t. And then position is ball dot position equals ball dot position plus ball dot velocity delta t. It's just from the start. So for the gravity plus drag, this is our B value, which I'll show how we got. And then for the Fnet, you have to include Fg plus F drag because now there's F drag. You can see that our real value really differs a lot, and our both computationals are very similar, and same in the X component. How I found B, I know M A equals negative mg plus bv squared, all in the y direction. So I just solve for B. We know we can solve for A in the y direction by using the first and the last two timestamps, and then we just find the final velocity and initial velocity and then solve for acceleration, and then we just plug everything in and then we get around 0.003. The mass is also 0.003 kilograms. Error, or let's first describe the system. The system is the paper ball and then the earth. The earth provides air resistance and everything else. We did not have, some error that may have occurred is we did not have a measurement in the y-axis, which could have skewed our measurements in the y direction and therefore our velocity. Also, the tracker app is not perfect, so it might have messed something up. The meter stick was also not perfectly horizontal, so it could have messed up some measurements as well. Questions? So velocity versus time graph. No, we did not predict our terminal velocity. Something that we could do is either shoot the projectile for a longer distance, or we can increase drag by making it like increase surface area, like a coffee filter or a parachute. And it should look like the velocity versus time graph should look like this. If we shot the object straight up and had the same initial speed as our experiment, it'd take longer to reach the floor because it's all in the y direction and not broken up into components. Thanks for watching.